I think everyone has their dinner now, and I hope just about done with it. We're going to go ahead and start our evening program, and I think we've got a very good speaker this evening, and I think you're familiar with him. Don, of course, has flown in space a number of times. He's had 2 space station missions, Expedition 6 in 2003 and Expedition 30 and 31 in 2012, and managed to get a shuttle mission in between. But in the course of that, he's, I think, taken a number of wonderful pictures, and perhaps tonight he'll show us a few of those. Let me turn it over to Don.
Thanks, George. It's always a pleasure to come here, and the conversation, particularly in this room, is almost better than the conversation in there. And oh, that's a picture of my home, away from home. And what I'm going to talk about is Astronaut's Guide to Photography in Space. And this is all geared so the next time you folks find yourself in space, you can use this guide to help you take better pictures. Because, you know, in the era of commercial space flight, you may find yourself in space and you want to maximize what you can out of that. So I'm going to give you a few pointers on how to take pictures when you find yourself in space. So one of the first things you want to do is to take a group selfie, right? I mean, you want to be able to tweet to all your friends and put on Facebook where you've been and look at this picture. Oh, I'm sorry. When I was loading the slides in the carousel, I got that in upside down. There. Now it's right. And the point is, in space, there's no hydrostatic up and down. And so people kind of float all over the place, and you will be working with your colleagues in all kinds of different orientations, and you will be taking selfies in orientations like this. And then you downlink these pictures, and what you find is people on Earth don't like to see pictures like this because, you know, you're looking at somebody upside down, and you're looking right into their nose, and you can count how many hairs are in there, and the shadows are all wrong. So, astronauts, we are trainable, and we are trained to take pictures like this. We can take such good crew photos that you can't even tell that we're in space. And so, think about this. When you find yourself in orbit, think about a combination of pictures where you can take pictures so that people on Earth can identify with them, but also take some pictures in an orientation in a way that shows what the real environment is like. Now, this is a picture from the Russian segment from their airlock, looking to the U.S. segment, and there, that little thing hanging down there, that's the cupola. And it's a collection of 7 windows put in a hemisphere, and these windows look down at Earth. And this is the kind of view you have. And we keep a few cameras in there, and the reason you have this many cameras is you keep them set up with different lenses and different exposures and shutter speeds and fades, simply because Earth moves by so fast. If you need to change things around, you may miss the money shot. So instead, you just grab another camera and start taking pictures. Another thing, don't turn your camera off. All of these cameras go into a standby mode, and they take almost no more electrical draw from the battery than if you turned it off. And if you turn your camera off and you stick it on a piece of Velcro, and then another crew member comes there thinking the camera is turned on and they want to do that money shot, they pull the camera, they take the picture, but the camera doesn't work. You pull it back, oh, it's off. You turn it on, and then you take the picture and it's too late. So just leave your cameras on. The batteries will not run down any quicker than if you'd turned them off. Now, here's a little video. I call it Photo Frenzy.
I'm Don Pettit. We're on the International Space Station in the cupola module. It's our window to planet Earth. Here we are, 7 windows and 8 cameras. It doesn't get any better than this.
You don't mess around. You take
No, and I'm mapping. And I've shot faster than my card can take. So I switched to another camera.
You want this card and this other D3 here?
Yeah, go ahead. Oh, there's Great Salt Lake. Look at that.
It is salty.
Oh, look at the fire. Look at that, man. The place is burning up.
Yeah.
That storm is awesome. Look at this, man.
Oh, that's...
Yeah, is that with the fisheye?
That's the fisheye?
That's a fisheye. See, I am just a wide-angle person, man.
Yeah, I'm with you.
You know. Okay.
You're that far away. You don't get the windows in there, are you?
Oh, I am getting the
Okay.
window. See, that's half the effect with the fisheye is you get the windows. See, look at that.
Oh, yeah.
See, look at that picture. See, so you get the whole Mother Earth effect.
Dude, I'm gonna be all about the fisheye.
Oh man, that is so
Oh yeah,
good.
that's money right there.
Yeah, that is money. This is gonna be a cover of National Geographic. You know, that'd mean more to me than getting Astronaut Hall of Fame. You know, who cares about that astronaut stuff?
I don't know.
So that shows, actually a photo frenzy is a good description when there's a spot on Earth that you really want to photo document. It moves by so fast, you are continuously taking pictures with any number of cameras with different lenses. Sometimes you have 2, maybe 3 crew in there all taking pictures. That was Joe Acaba. When he came up to join us, and Expedition 30 turned into Expedition 31. And it just a little dynamics for how you take your pictures when you're in the cupola. Now, you could take wide-angle views of Earth, and this is one of my favorites because the cupola allows you to look at the limb of the Earth so you can see wide scale, the curvature of the planet. If you just have a nadir viewing window, you're looking straight down and it's hard to see the edges of the Earth. And so you could take these side viewing windows in the cupola with a wide angle lens and you can record Earth on the length scale of half a continent. And when you do that, you can see detail that escapes observation if you're just flying in an airplane or if your feet are on the ground. So think about wide angle obliques as well as telephotos. So this telephoto picture was taken by a crewmate of mine, Anatoly Evanesian, and it's of Manhattan, and it's a really neat photo. But you could get yourself in the mindset of, why should I take a telephoto picture of Earth when I can do this? I can go to Google Earth, and I can get the same picture from Google Earth. And the resolution will probably be greater in the Google Earth picture than what you do from station. So you could say, why do I even want to take a picture with a telephoto lens? Well, here's why. Look at this picture. One, there's no shadows. And that's because satellite photography of Earth is designed to record their information during local noon, specifically keep shadows from being in the picture, because the whole point of this is to look at detail on the surface of the planet, and you don't want shadows. And these are all mosaiced pictures, dozens of pictures mosaiced into one, and because the people who design this say the only thing of real interest is the land. They do a great job of mosaicing on the land, but look at the Hudson River, look at the East River, that you see these mosaicing artifacts. So now compare that again to Anatoly's photograph. Look at this. You see the real river. You see low-angle sun. Look at the shadows from the downtown region, and you see shadows projected out into the water. So by virtue of being a human being, running the camera, looking at Earth at different angles, you're not a machine that's pre-programmed. You can add an artistic flair to the picture. So remember, use the telephoto lenses. You can get imagery that has a different flair than what you pull off of from Google Earth. Oh, this is a picture of Earth, and that is a specular reflection from the sun. We call it sun glint. It's really, really bright. You almost need sunglasses to look down at that because it's blinding. And satellites are pre-programmed not to look at sun glint because it's almost like pointing your camera at the sun. And any fool knows you don't point your camera at the sun. So they turn satellites off specifically to avoid specular reflection off the water. But of course, we're astronauts. We don't have enough sense to know you don't point a camera at the sun. So we go ahead and we take pictures in the sun glint, and look at that. You see detail in the water that escapes normal photography. There could be variations in height in the ocean and on lakes and rivers that are centimeters in length scale, and because it's a specular reflection from the sun, this detail shows up. And nobody knew that this detail was there until astronauts happened to take pictures looking at sun glint. And oh, this, by the way, all that looks like glacier ice, that's ocean. And this is off the coast of Mozambique. And so you could see all of this structure in the ocean, which is invisible in any other way. And once human beings make this discovery, then you can pre-program satellites to not only take more data, but better data than what a human being could do. But sometimes when you're in a frontier environment, it takes the mind of somebody that doesn't really know what they're doing or why they are there to make a discovery, and after that discovery is made, then you can make a machine to really collect the data. So keep that in mind when you find yourself in space. There may be some really unique circumstances where you can make some observations, and even though dozens of people have been there before you, you could see something completely new. Oh, this is one of my favorites. Nighttime photography is one of my favorites. I'm an amateur astronomer, and I love to take pictures in the dark. And this is a picture in the cupola of the setting sun. And so you think, wow, that's neat, a setting sun. But let's contrast that environment with what we're used to on Earth. The sun, it's a 1/2 degree in the sky. It takes 2 minutes for the sun to set on Earth. And so you've got time to pull your camera out from your pocket, your smartphone, and you can type in the code, and you can take a selfie or two, and then you can take a picture of the sunset and you won't miss it. On orbit, the sun, the disk of the sun sets in 7.5 seconds. So you have to be ready. Your camera has to be turned on. If you see a sunset, you grab the camera to take a picture, and your crewmate turned the camera off, guess what? You missed the picture. So you got to be ready. You got to take the picture, and you can get some spectacular sunsets on orbit. But wait, there's more. Notice the color. It's kind of more orangey red. And there's a reason for that. Imagine that you've got a sphere, that's Earth, and you're a little stick figure standing on the top of it, and you're looking at the sun setting, and the ray coming from the sun is like a tangent ray laying against the sphere. And then you've got this fuzzy atmosphere around that the tangent ray is going through. And from your vantage point on Earth, you are only seeing a half an atmospheric pass for that ray of sunlight. But when you are in orbit looking at that same tangent ray, you see a full path length through the atmosphere, because the atmosphere preferentially scatters blue light out, which is why the sky is blue, and sunsets are yellow, orange, red. When you are in orbit and you look at a sunset, it has a different suite of hues to it than the same thing that you are used to seeing on Earth. So pay attention to that when you find yourself in orbit, and be ready to take pictures of the sunset, 7.5 seconds, and also make sure you got the color balance. Know how to deal with the color balance on your camera so that you get the real colors of the sunset, because they're going to be different than what you have ever seen on Earth. Oh, Aurora. This is one of my favorite subjects to photograph. And Aurora, the first order, is easy to take a picture of. But the second order, it's hard to get a good picture. And part of the reason is the difference between the red and the green. And this is all due to atomic oxygen, right, in the upper atmosphere. And the green is at 557 nanometers, and the red is at 630 nanometers. And the green is 8 times brighter than the red. In camera vernacular, that's 3 f-stops. So if you set the camera up to take a picture of the green, the red, you just get this little wimpy red. But if you take a picture to get the red, the green is saturated, it's burned out, there's no detail, it looks awful. And maybe on a rare occasion, the red and the green are balanced. But most of the time, it's not. So what you have to do, you have to know how to set your camera up to do high dynamic range imagery, where in rapid succession you take 3 to 5 pictures, each maybe an f-stop apart, a factor of 2 apart in exposure. And you'll get the red in one of the pictures, you'll get some of the green in another picture, and then you'll get the brighter part of the green in another picture. And so you have 3 to 5 pictures, and then putting them all together after you come home, because, you know, astronauts spend most of their time on Earth and only some of their time in space. And what do you do? What are you going to do in all your spare time once you come back to Earth? Well, you can work with your 500,000 or 600,000 pictures you took, and you can work with these putting together these high dynamic range pictures. This is another aspect of Aurora. The green is at a low altitude. It's around 120 kilometers. And your orbit's at 400. And so you fly over the green, but the red is at your orbital altitude. So you fly through the red and over the green. So when you are submerged in the Aurora, you look out a nadir window and you see green. You look out a port or starboard window and you see red. It's like you've been shrunk to some miniature dimension and put inside of a neon sign. And I've got a short video, a short movie of flying over Aurora here. And it almost looks like a glowing diaphanous river that you flow over. And you can't record this with video cameras. They're not sensitive enough. So you have to know how to set your camera up for intervalometer, where you sequentially take a picture every half a second or maybe once a second. And you take thousands of these pictures. And then later on, after you come back to Earth and you got all this time, you can put them together as where each picture makes a single frame in a movie. So a 20-second movie may have 2,000 separate pictures that you've taken. Oh, this is a reboost on station, and we do this about every 3 to 4 weeks, where you fire the engines. And this was a reboost done by a Progress vehicle docked to the aft end in the Russian segment. And you can also see Orion. You see Orion up there, the constellation. Almost looks like we're actually going someplace other than circles around Earth. But this is actually how we pay for our solar power. Because you think, wow, solar panels, we have 100 kilowatts on station. All those solar panels, well, there's a lot of surface area there because you need surface area to generate power from the sun. And there's still a residual piece of the atmosphere, an exponential tail for the decreasing density of the atmosphere. And all those solar panels make enough drag that station loses about 100 meters of altitude every day. 100 meters. So after 3 to 4 weeks, we need to get our Russian colleagues to fire up Progress and reboost station. So the cost of this free solar power actually is paid for in chemical energy and rocket propulsion. It's just something to remember. There's nothing actually free in this world, right? But it does make a great topic to try to photograph. Visiting vehicles. This happens to be ATV, the European cargo vehicle, coming up to do an automatic docking on the aft end of a space station on the Russian segment. Although cosmonauts are trained to be able to take over and do a manual docking. And when ATV comes up, it sort of parks off at about 10, maybe 15 meters, and it just sits there. We call it station keeping, maybe for 10 or 15 minutes, and then it comes in and docks. And during that time is a great time to take pictures. And it's kind of like two dragons that are snorting fire to see who can make the biggest display, because to maintain this juxtaposition of two vehicles with orbital mechanics requires periodic firing of your reaction control jets. And I made a little movie of this. Let's see how it plays. And if I was really, really good as a photographer, I would have made the photography of the jet firings actually sync up with Verdi's Requiem. But maybe next time I can get the flight controllers to change the algorithms for firing the jets so that we can sync them up to the Requiem. This is another favorite type of photography. This is star trail photography. And I did this on a geology field trip exercise. That's SP Crater in the San Francisco volcanic field north of Prescott, Arizona. And they send us there periodically to do field geology, where we pretend we're walking on the moon, and there's a lot of basalt and other things to map. And anyway, we go there to learn about rocks. And I stayed up one night because the nights are clear, and did this classic star trail amateur astronomy photograph. You put the camera on a tripod, you point it up at the sky, and then as Earth rotates, the stars move in the sky, and of course they're rotating around Polaris, which is the center point of the rotation. Now, knowing that this is a standard thing that amateur astronomers do on Earth, it's only fitting to do the same thing on station. So here's a star trail picture on station. And not only is this kind of a cool looking picture, but the natural phenomenology, the physics involved in this picture. Each one of these pictures, I could talk about the physics in a picture like this for about a half hour. And I only have 5 or 6 of these pictures. So, fortunately the bar is still open. But anyway, to quickly go over what we have here, you see the stars are going in circles. At the first order, you say, oh, that's Polaris, like the stars going in circles on Earth. And it's like, minus 10 points. That's not it. Station, the belly button on station points towards Earth as it goes around, which means every orbit station goes around Earth, it spins once about its center of gravity, and it rotates about the pitch axis. So the stars are rotating because of the one revolution of station every 90 minutes about its pitch axis. So that's the pitch axis of station pointing into space, and the direction is the complement angle, which is 90 minus 51.6 degrees projected into space. So that's not Polaris, and it slowly precesses with every day. What else? Oh, you can see the limb of the Earth. That green thing that's laying on top of Earth, that kind of looks like a slice of key lime pie. That's the atmosphere on edge, and it's glowing green. The scientists have a word for that. They call it air glow. And why do you call the atmosphere that glows? Well, the answer is air glow. And it's the same wavelengths as Aurora, but the excitation mechanism is completely different. And that scale height is about 120 kilometers. So that's actually entry interface in terms of astronaut vernacular. That's where your spacecraft starts to enter the atmosphere. That's where things start to get hot. That's where meteors burn up and become meteorites. Is right at the beginning of that little green slice of key lime pie. And you can notice sort of a faint reddish hue above that. That's also air glow, and that's up at a higher altitude. That's actually at space station altitude. Now, what's all that stuff on Earth? And let's look at this picture. Again, you can see the key lime pie air glow. You see circles on stars. But those streaks on Earth, those are cities streaking by due to a combination of Earth rotation and orbital motion. And then, what are all those flashes? Those happen to be a single thunderstorm as a function of time. So it goes flash, and then there's motion, and it goes flash again. And so you can see a time history of a single thunderstorm in there. And then what's even cooler is look at the stars as they trace through the atmosphere. And you can see as the stars get deeper and deeper into the atmosphere, the curvature changes. And that's because the atmosphere density is increasing, the refractive index increases with density, and it acts like a lens. So there's all kinds of really neat stuff that happens in here. Or you could just sit back and enjoy it as being some art form. Now, these are made from sequential, there's about 30-minute pictures. But it's hard to get a 30-minute picture with a digital camera. Shutters typically max out at 30 seconds, and that's because the electronic noise can build up, and after a 30-second exposure, it's not very nice anymore. And so these 30-minute pictures are made from stacking up sequentially 30 minutes worth of 30-second pictures. And because they're made out of all these sequential pictures, you can make a movie out of it. So let's watch the movie. So look at that. You can see how things are summed. And look on the right, there's a thunderstorm coming in. And you can see the stars are drawing trails. That was a coastline. And then here's looking port side, and you can see how the stars make circles along the port axis of station. Really neat stuff. Let's look at a few more of these. I like this because it has space station structure. It has the Soyuz and the Progress vehicles. And you can see Aurora, you can see a sunrise, you can see lightning, you can see cities. There's a lot of neat stuff in these pictures. This picture, this is off the coast of the Falkland Islands. And off the coast of the Falkland Islands, way out in the middle of the ocean, are all these oil platforms. And you could be floating over these things at nighttime, and you look down, and on every oil platform is a bright xenon light, because they're well lit. And you look down, and you think that you're looking at stars. You think there's constellations, but you're like, I'm looking at the ocean, and I'm seeing stars. And you're not seeing stars, you're seeing oil platforms. And so in time exposure like this, the oil platforms with their really bright xenon lights make those streaks. And then you can see the Japanese segment there. And that little conical shadow on the Japanese segment, that's a shadow of the sun cast by the cupola, where I'm at taking this picture. And what's even cooler in this picture is, see that little flash that's kind of up on the right-hand side in the atmosphere? That's an iridium satellite flash. And so there's a whole constellation of iridium satellites. We use them for sat phone communication. And they have a flat antenna which can reflect sunlight, kind of like a mirror. And if you know the right location on the Earth when one of these satellites are sunlit, they will make a flash in the sky lasting maybe 3/4 of a second that's as bright as Jupiter. It's really amazing to see these. There's a program that can predict this, and you can get brownie points by taking all your friends out when you know one of these is happening, and you say, look up at the sky, I'm going to snap my fingers, and you'll see a flash. And I happen to know the amateur astronomer that wrote that software. And by the way, you find these on this program. It's run by ESA. It's called Heavens Above. And it's a great program for doing any kind of satellite tracking. But if you're typing that in the internet, make sure you're careful about how you type Heavens Above, or you might get a different kind of website. But Rob Mattson from SAIC wrote the software for predicting that. And while I was on station, he sent me an email and said, if I modify my code so I could predict an iridium flash on station, would you be willing to take a picture of it? And I said, great, do it. So he wrote his code, sent up 3 or 4 predictions. I set all these cameras up. Nothing happened. So I sent him an email. Nothing happened. So he reworked his code, sent up some more predictions, set up cameras. Nothing happened. We worked back and forth for about a month, maybe 5 weeks. And it was at the point where he'd send predictions, I wouldn't even bother to set up a camera. And then finally, I went to look, and there was flash. It's like, oh, he got lucky. So I looked at the next one, flash. He nailed the software, the mathematical calculations for a narrow beam of light. It's only about 2 kilometers in diameter where you can see an iridium flash. So imagine one satellite with an antenna reflecting a beam of light onto space station, and they're all moving and all of that. And he nailed the calculations, but it took us like 4 to 5 weeks of iteratively working together to get to that point. So that's another thing to think about when you're on station taking pictures. You may not be successful the first time. And it's the same thing with experiments, science experiments, utilization on station. You may not get your science correctly done. You may have something go wrong in your apparatus. And that's one of the neat things about space station is we have the time to do iterative experiments on the station where eventually we can bring things to a productive endpoint simply because we can do it over and over and over again. Oh, this is this is another recent phenomenon on Earth. We're switching from blue-green mercury vapor lighting and the yellow-orange sodium vapor lighting to LED lighting. And you see these bright pastel colors, intense colors coming out from many places in the world now. And it makes great photography like this. They're beautiful. It'll be interesting to see what this does to our nighttime skies in terms of people on Earth wanting to look at the heavens. Now, this is one of my favorite pictures of Earth. It's the Mother Earth view. And on a high contrast LCD display, the colors are just really intense. It's amazing to see this. And I got the thought, what happens if you make this into black and white? What happens if you're in this technicolor, greater than technicolor environment, and you start shooting black and white? So I played around with that. And what happens when you see a black and white version of one of these images, your eyes focus in on different detail. So here's one of the star trail pictures, just intense Kodachrome moment, but in black and white, your eyes focus in on different things. So think about when you're doing photography in space, trying something else, black and white photography, and you know, you're always doing color photography, and you make it into black and white once you come back to Earth, so it doesn't cost you anything. But this is a region of the Betsuboka River Delta in Madagascar, and you know, choose patterns that look interesting, make them into black and whites. This is ice pack melting off the coast of Greenland. Almost looks like milk drops in a glass. And this, I call this Godzilla in space. And it's so fitting because you have Canadarm there with the SPDM and the shadow projected on the Japanese module with the Japanese flag. I mean, it's perfect. Godzilla in space. And then rendered in black and white. It's primarily a black and white subject anyway. So I stripped the color out, but I left a little bit of color in the Japanese flag just to show that. And then this, I call this my business suit. And when you're getting ready to go for a spacewalk, this is the kind of suit you need to wear for doing that kind of business. Not this kind of suit, but that kind of suit. And I like the tones of whites that you see in a high-key picture like this. You focus on a different subject other than the really bright red ventilation ducts and other things that tend to make these pictures cluttered if you keep them all color. Now with this, this is second to the last slide. This is an example of why we need to share our data. And NASA has this archive where all of the pictures are available to the public. Public domain pictures. You don't need to pay them any money or anything. You just go to the website and you download the pictures. And one of the reasons you do this is because there are people out there that have different ideas and different thought processes than you, and they may be able to do something with the data that you never even dreamed of. And so this is a data work done by Nathan Bergay, who is a data analyst, then working at Portland State University. And he did a silly thing. At the time he did this, there was 1.2 million pictures that had been taken looking at Earth from space station. And he got the database. He deleted all the pictures. Who cares about what the pictures are of? And he took the latitude and longitude of every time an astronaut clicked the shutter and took a picture of Earth. And then he plotted that longitude and latitude, 1.2 million points on a plate Curie projection of Earth. And of course, he chose a plate Curie projection because it doesn't have the singularities at the poles like a Mercator projection does, and you can go up to 51.6 without getting a lot of distortion. And so there you have it, a map of Earth with a data point, latitude and longitude, of every time an astronaut decided to click a shutter while looking at Earth. And you see the outline of all the major continents. And you see a lot of black in places that astronauts deem really cool to take pictures of, like Hawaii, and there is the East Coast and Bahamas. You see the Middle East, you see a lot in Europe, you see Japan. Australia isn't really well covered there. You see Africa. Now, what's also interesting is where you don't see pictures. Like, look at the Amazon River Basin and the Congo. And I thought, well, why aren't there a lot of pictures there? And it finally dawned on me, after a crew member takes, 20,000 pictures of clouds over the Amazon or clouds over Congo, you figure, I've got enough pictures of clouds, and they stop taking pictures. And so a lot of the high density spots are places on Earth that aren't always cloudy. So I like to use this as an example that there's more to taking pictures when you add the human element into the exploration plan. There's something essential about being a human where there's something in the universe that says, this is interesting. I have a camera here. My crewmate left it on. I'm going to take a picture. And it also shows that there are people who think differently than those here at NASA. And if they have access to the database, they can parse things in a way that somebody at NASA would never even dream of doing this. I never would have dreamed of taking the data and stripping out all of these beautiful pictures that we worked so hard to get and only looking at the latitude and longitude. It takes somebody else outside of the program to think about these things. And so we were part of Group A, which, according to my little paper here that I was assigned, Group A is supposed to be on cooperative research, which we spent most of the time herding cats. But other than that, we were talking about how to share all this data, not only between researchers so we don't duplicate our effort, but how do we share this data so people outside of the program can have access to it, because maybe they might have some ideas that we don't because we're looking at it from the inside. And this is an example that we are doing this with all the imagery from Space Station. So this is my last slide. This is a self-portrait, by the way. And the way I did this, you set the camera up in the Russian airlock, you get it all focused on the cupola, and then you put it on time delay, and then you fly as fast as you can through the service module, through the FKB, into PMA1, through node 1, make a hard left turn, go into node 3, go by the treadmill, squeeze by the toilet, go duck your head so you don't hit it on the A-red, and then you dive down into the cupola and stick your head up there, turn on a flashlight so you can light your face up, just in time for the camera to take a picture. And everybody wants to do this, and plan on taking 400 or 500 pictures before you get one right. But this is also a good picture to kind of philosophize about why are we there and what are we doing, and exploration is something fundamental to human beings, and being on the frontier, it has this aspect of the answers are not in the back of the book. You may have to figure something out for yourself. And this is discovery, and this is why at least a small fraction of our society seems bent on doing exploration. And it's a good thing it's only a small fraction, because if everybody were explorers, we'd all starve. We'd be naked and we'd be starving to death, because we need a lot of people to raise food and do all of those things. But we need a small fraction of our population to think about what's over the hill or what's beyond the next planet, because that's what ultimately gives us new places to live and resources to use. And part of being an explorer is documenting the story and sharing it with everybody back on the planet or everybody back on the continent that didn't have a chance to do the exploration, so they could be happy, making food and making clothes and making all this stuff that we need to keep society going. So you need to share the story, and one of the best ways to share the story is with photography. So remember that when you get your ticket to ride on the commercial spacecraft and you're going to go into space and you're going to be taking pictures, think a little bit about how to take the pictures, what subjects to take pictures of. Think about strategizing your photography so that the pictures may not be ready right out of the camera. You may need to do a little work with them when you come back to Earth. Thank you. If we could turn up lights, if folks want to ask a few questions, I'd be happy to answer questions. Yes.
Were there any photography techniques that you learned on station and then brought them back down to Earth after you learned them up in space?
Photography techniques that you learn on station. Well, the basic techniques of photography in space are the same as down here. It's all about composition and exposure and focus, but the subjects are different, and the possibilities for what you take pictures of are different, and most of the basic photography skills I had from just hobby work here and from the photo TV trainers that we have at Johnson Space Center. We've got some of the best photographers in the world that work at Johnson Space Center, and they have a lot of patience for astronauts that maybe some of them don't know which end of the camera to look through. And so they have patience to teach us so that by the time we do get in orbit, if we take 500,000 pictures or so, there'll be a few good ones. Any other questions? Yes?
Did you photograph anything that you couldn't explain, that you found? Photograph anything that was unusual that you couldn't explain that makes you uncomfortable to share with us?
Did I take pictures of alien spacecraft? That's how I interpret that question. Fortunately, I didn't see any alien spacecraft. Maybe the closest thing to an alien spacecraft was the ATV that came up to dock. But other than that, there are things that you see in space that you can't explain, points of light and things like that, and later you find out that, that's commensurate with the Hubble telescope orbital parameters. And there's I have some pictures where I actually caught the Hubble telescope streaking by, and it was strange because it was above all that green in the photograph. And that's because Hubble Space Telescope is at a high altitude, and it's like, what's up there? And actually my friend Rob Mattson at SAIC looked at those pictures and correlated it to the orbit of Hubble Space Telescope. So there are things that you can't explain, at least at that time, but ultimately it's all explainable. Yes?
Here you go.
What was the time delay on the camera for that, and how many shots did you really have to take to get
Actually, what I did, I didn't set a time delay. I set it for an interval, and I set it for a 2-second interval. So you just turn the camera on and it's going click, click, click. And so that you could you could swing by the galley and have a cup of coffee before you popped into the cupola. I just thought it would make a better story if I had everybody thinking that you know, it was one picture. And so what you do is you pop your head up in the cupola, and you know that every 2 seconds another picture is being taken. And so you've got this little flashlight, and so you vary the exposure on your face because you don't know how much light to shine on your face, because if you didn't have a flashlight in there, you wouldn't be able to see inside the cupola, because the main exposure is for the stars outside, and the cupola is dark, and so you have to play with the light intensity to get it just right. And so you're in there knowing every 2 seconds another picture is being taken, and you're messing with putting your fingers over the front of the flashlight. And so I literally took about 400 pictures to get this one good one. But that's the plight of almost any professional photographer, right? I mean, how many pictures does a real photographer take? And I think the only reason they can get good pictures is because they take so many, they're bound to get at least one good one. Mike.
So I think you're reminding us all that one of the biggest forces of discovery is a naturalist with a notebook. And your notebook is kind of the camera. We are really well equipped with camera gear. I can't imagine the number of pounds of camera gear we have on station. When we go to the surface of the moon or Mars, we're going to be much more constrained, and photography may be even that much more important. Are you talking to?
Yeah, you know, you look like in the Orion capsule right now, there are trade-offs of mass, and we could be flying Orion to the moon without even having a camera. And you know, we're just in the middle of the kind of standard NASA engineering food fights, and it won't turn out that way. But it is something that, from a public interest point of view and sharing the story, and also from the scientific point of view, having a significant photographic capability, I think, is essential when you're doing this kind of exploration. And fortunately, the cameras now, almost any professional level camera can do video and still photography. And so you don't have to have a big video camera and a film camera and low resolution digital camera like we used to fly on the shuttle. Now you can just fly one or two camera bodies and a number of different lenses, and I think you could adequately cover what is needed in terms of recording. And I hope when the food fight is over that we have that level of photography equipment, not only in Orion, but wherever we go from there. Any more questions? Yes.
Yes, you showed a number of pictures like of Iridium, and you mentioned Hubble on low Earth orbit, on essentially circular orbit. Did you see any highly eccentric orbits of like satellites that have a long hang time over North America or the Northern Hemisphere and pass very quickly about the South Pole?
Good question. I haven't seen anything like that. Just with my eyes. There are a few interesting lines that are going contrary to the star motion that show up in some of the photographs, and maybe you could only see that line for maybe a third of the frame, and then it just disappears. So maybe that could be an explanation for what you see. There's a lot of information in these photographs, and the more you understand about your environment, the more detail you could see. And that's an interesting point, and I'll have to look through some of my pictures to see if I could see any of these sort of halo kind of orbits with a low perigee, where they just really scream close to Earth, going really fast, and then they slow way down. Pat.
Wait for the mic.
So a lot of audio files now go back to vinyl, and they swear by vinyl that the sound quality is better, etc. From an artistic point of view, do you see anything lost from film photography versus digital photography that would be an advantage here?
I think overall, there's a gain with digital photography. The sensitivity of the chips, the dynamic range is amazing, and it's improving every year. Every camera that comes out new, a high-end professional camera, is maybe 1 to 2 f-stops faster than the previous generation. And then the dynamic range in terms of how much it can record from blackest black to whitest white without exceeding its ability to record. That is also improving, and it's much greater than film. Having said that, there's a certain artistic quality, particularly with black and white film. And you print it on something like Ilford paper, and you look at some of these prints, and they're just amazing. There's almost a three-dimensional structure when you look into these black and white pictures that I find just incredible. And it's kind of like sailboats versus steamboats, right? There's always going to be a crowd that wants to do a sailboat, even though it's basically an obsolete technology. And I know Mike's going to clowy me on that because he's got a sailboat. But you know, there's always going to be a film crowd, particularly for black and white, because the chemistry is so much easier to do than color film. And there will always be an amazing dynamics with black and white. When you're in a frontier environment like this, digital is the way to go. Film gets fogged by galactic cosmic rays. We talked about the radiation effects on people here this afternoon, and the general consensus, they hadn't found any effects. Well, it's not true with film. And we learned this after Columbia. Ken Bowersox, Nikolai Budarin, and I were on station during Columbia, and most of our mission up to that point was taking 35 millimeter film and 70 millimeter film. And we had a pseudo-archaic, by today's standards, digital camera. And after Columbia, we stopped using film because we knew it was going to be years before we were going to be able to rotate film. We knew it was going to become fogged by galactic cosmic rays, and we switched 100% after Columbia to digital imagery, and NASA's switched over, and nobody's gone back to film, at least on orbit in the frontier. Kaz.
Yes, your Aurora pictures are magnificent. And how do you compare the brightness of Aurora when you look at them with the naked eye?
Aurora with your naked eye is not nearly that bright. And the color saturations aren't nearly that intense. Weak Aurora looks sort of like a thin green veil, and sometimes you can't even see the red, and then you take a picture and it's like, wow, look at all that green, and then you can see the red that you couldn't see with your eye. That's not all the time. Sometimes you can have some really intense auroral activity, and that's a time when it just blows the detectors out on the camera unless you start to use faster shutter speed. So it can be both ways, where the aurora is fairly faint. The air glow is really faint. You have to be well dark adapted to see the atmospheric air glow, but it shows up readily in photography. Any more questions? George, I think we need to call it a night.
I think so. Well, thank you very much, Don. That was great.
Thanks, George.
I think that completes our program for today, and